Welcome once again. We are here with Stem Cells Unveiled from Basics to Breakthroughs. I'm Dr. Sukant Khurana, your host, and we are on episode number 3, Sources and Harvesting. Where do stem cells come from? Once again, I'm thrilled to have brilliant Basudha Banerjee, our resident collaborator on stem cell biology, leading the charge. Basudha, take us into the world of stem cell origins.
Thank you, Dr. Khurana. I am so pumped to be back. After diving into how stem cells work last time, I am itching to explore whether we actually get these incredible cells from. Like, where do we actually get them from? It's like tracing the roots of a tree, the natural sources, or lab innovations. The whole process fascinates me. So, let's get started with where stem cells live in the nature. Dr. Khurana, want to toss out the first source that comes to your mind?
Well, you're setting the pace, Vasudha. I love it. I would say embryonic tissues. Those pluripotent powerhouses from early blastocytes are the big one. But you've got the floor, run with it.
That's the perfect starting point. So, embryonic stem cells, they're indeed a gold mine. They come from the inner cell mass of the blastocyst, which is approximately 5 to 6 days post fertilization. These cells are so versatile, capable of becoming virtually any cell type, which is why they have been given a research cornerstone. But it's not the only natural source. Uh, I would also like to add that embryonic stem cells, they have a lot of ethical concerns attached with it. So I'm a huge fan of the bone marrow. So it's like a stem cell factory. As I previously mentioned, I was working on mesenchymal stem cell isolation from bone marrow. Apart from that, bone marrow is a house of hematopoietic stem cells. They hematopoietic stem cells, they churn out blood cells and mesenchymal stem cells as well, which can form the bone, cartilage, you name anything. So basically, it is like bone, cartilage, and so it's incredible how accessible the bone marrow is for therapies like transplants for leukemia. And what else would you like to add to the natural list?
Bone marrow is a classic art through umbilical cord, blood, rich in hematopoietic stem cells and easier to collect than marrow, especially right after the birth.
Absolutely. And the cord blood is a gem. So parents can bank it at the time of birth, and it is less likely to cause an immune rejection in transplant. So that's a win-win situation. Another favorite of mine is the adipose tissue, the fat, basically. It's packed with mesenchymal stem cell, and all it takes is a quick liposuction to harvest them. I mean, who knew fat could be so useful? So these natural sources, the embryonic, the bone marrow, cord blood, and adipose, they all are so diverse, each with unique strength. But let's pivot to the laboratories now because that's where the things get really wild. So, Dr. Khurana, want to introduce the lab created options?
Sure thing. Induced pluripotent stem cells, iPSCs, are the stars here. Reprogramming adult cells to act like embryonic ones. It's revolutionary. Over to you to unpack that.
Oh, so iPSCs, they're sort of my obsession. Imagine taking a skin cell, something as simple as a fibroblast, and hitting it with a cocktail of transcription factors, namely OX4, SOX2, KLF4, and CMYC, which are commonly known as the Yamanaka factors. So suddenly it rewinds to the pluripotent state and capable of becoming almost anything. So here the fibroblast got reprogrammed into a pluripotent state. Shinya Yamanaka's team cracked this in 2006, and it has been a game changer since then. No need for embryos, fewer ethical hurdles, and you can make patient specific stem cells for research or therapy. So, Dr. Khurana, what's your take
Yeah.
on the reprogramming magic?
Yeah, so time travels is a perfect analogy. It's not just pluripotency, it's how iPSC let us model diseases in a dish or test drugs on patient derived cells. It's pure genius.
I totally agree with you on this. So, disease modeling is huge, but let's talk about the nitty gritty. Getting these cells isn't always a walk in the park. Collecting embryonic stem cells involves donated blastocysts, often from the IVF clinics, which is a tightly regulated process. Bone marrow aspiration. It's invasive and sometimes painful, honestly. Then we have adipose, which is easier, but cord blood requires planning at birth. Then we also have iPSCs. Don't get me started on reprogramming challenges. Early methods used viruses to deliver those transcription factors, risking mutations as well. And I've heard of labs that are struggling with low programming efficiency. Sometimes only 1% of the cells convert. So there is a very big challenge that is currently with the researchers. And would you like to mention any hurdles that you have come across, you have heard during the sourcing of stem cells?
See, most of my stem cell work is obviously indirect with collaborators and other researchers. One of the bad things of becoming an entrepreneur is you may have a lot of labs working under you, but you're not directly involved. But I'm still aware of all the challenges. Culturing, it's sourcing is there, but then there's culturing is a whole different beast, right? Maintaining pluripotency without spontaneous differentiation is a very tricky business, and contamination is a constant worry. In fact, another Basudha I knew, there was my sort of classmate. I was an integrated PhD student at NCBS, and she was PhD. You can call batchmate or 2 years senior. We had the courses together. She joined someone called Mithridas Panikkar, who was at NCBS. Then India, with its petty politics, Panikkar had actually the India's lead in stem cell biology. I'll not go into how his work was sabotaged, and he's eventually moved to California. But she, with her boss, was doing a lot of this thing, and I thought most of her struggles were related to dealing with spontaneous differentiation. And shockingly, against research interest, what was pushed through was work on Drosophila stem cells, just because there was Drosophila lobby, while the initial work had started with human stem cells and very amazing work. But yeah, I am aware with someone who used to be a good friend. I'm not in touch with her anymore. A lot of other stories, but anyway. But at that time, she was a good friend of mine. And I realized the challenge of maintaining pluripotency. And then I see now with my collaborators having that challenge, and in India more so than my US collaborators, because of contamination issues being bigger here. Over to you, Vasudha.
Yeah, I mean, that is true. Culturing is where the real art comes in. So you need precise conditions, growth factors, specific media, and feeder layers as well to keep the stem cells happy. And embryonic stem cells and iPSCs are especially finicky. Take non-viral reprogramming using mRNA or small molecules to avoid all those risky viruses. Or we also have the 3D culture systems that are gaining attention, like bioreactors that would scale up the cell production. I've been geeking out over automated platforms that monitor and adjust cultures in real time. They seem to be game changers for the clinical grade stem cells. And anything new that you have currently seen in the field, Dr. Khurana?
Yeah, I mean, automation is huge. I'm impressed with cryopreservation advances. Freezing cord blood and adipose-derived cells without losing viability is getting better every year. In fact, one guy, again a mixed story, because that guy ran out of money and he even ended up not paying us. So there was a cheating, whether it was with bad intention or the guy going broke. I was aware of Indian origin, collaborating with some top Indian hospitals on a temporary visa to California. He tried to punch above his weight, and he was pitching for funding, essentially for cryopreservation. He was even doing some collaboration with some South American countries. There were even some ethical issues which he was trying to circumvent by going there. So I was aware of a lot of day-to-day functioning, and then the way his collaboration with me came in was not in that sphere, but I heard his uh, daily challenges. He discussed this. I told him I can't help him in this, especially with the South America thing. Like to understand things through like one country rather than multiple countries, how things can be done in US. But then we ended up working on some pandemic, and eventually the guy went broke, and a lot of my money wasn't paid. And not sure where he's vanished. He's currently, I think, doing some petty jobs in California. But I was aware of even internationally how people were trying to pitch in, and around 2017 onward, the cryopreservation has been a big business. In fact, money-wise also, I guess again last year a lot of good companies got funded on this. So it's a big deal. Over to you, Vasudha, on cryopreservation.
Yeah, cryopreservation, it's like putting stem cells in a time capsule for future use. So, wrapping this up, I'm just amazed at how far we have come from harvesting to engineering iPSCs. It's setting the stage for everything we'll cover in this series: therapies, tissue engineering, and a lot more. So, Dr. Khurana, any final thoughts on where this all leads?
Yeah, so you have laid out a very fantastic map, Vasudha. The sources and innovations are foundation for turning stem cells into reality. Can't wait to see where we go next.
Me neither. Thanks for letting me steer this, Dr. Khurana. It's been a blast diving into details. And honestly, I could talk about stem cells and stem cell harvesting forever. But let's save some time for the later episodes.
You've been phenomenal, Vasudha. That's episode 3, folks, led by brilliant Basudha Banerjee. Next up, we'll explore how stem cells are revolutionizing tissue repair. If you've got questions, please write them in comment section. Share this podcast widely. Subscribe to it. We'll meet you again. Thank you, Vasudha. Thank you, listeners. Bye bye.
Thank you.